In this video, we will learn about function transformations. In other words, how the graph of a function can be stretched, shifted, and flipped across the Cartesian plane. First, we must review the 5 functions that we will be transforming. These are often called parent functions. First is the linear function. We've already inspected this function in previous videos. Notice how the domain stretches from negative infinity to positive infinity, and so does the range. We call this an increasing function since it moves upward from left to right. Next, we have the absolute value function. Again, the domain goes from negative infinity to infinity. However, the range is only from 0 to infinity. This means I can put in any x value that I want, but the only thing this function will spit out is some number greater than 0. If you read the function like a book, from left to right, this function is first decreasing, then increasing. Next, we have the quadratic function. This looks like the absolute value function, just a little bit more curvy. Notice it has the same properties as the absolute value function. You can put any x value in it, but you'll only get a y value greater than 0 back. Next is the square root function. The domain and the range for this function goes from 0 to infinity. This means you can only put numbers greater than 0 into our function in order to not break it. And it will only spit out numbers greater than 0. Although it may be hard to tell, this function is also increasing from left to right. Lastly, we have the cubic function. This function has a domain and range from negative infinity to infinity. It's also increasing from left to right. Okay, now that we know what the parent functions look like, let's review ways we can transform them. First, there are vertical shifts. Let f of x represent any of the parent functions. Then, if we add some real number c to it, we can create a new function g of x, which is similar to our parent function, but vertically shifted upward by c units. For example, if f of x is the absolute value function and c is 3, then my new function g of x will be the absolute value function shifted upward by 3 units. Similarly, if I subtract my function by c, it will shift my function downward by c units. For example, if f of x is the square root function and c is 5, then I can create a new function g of x, which is the square root function shifted downward by 5 units. Next, we'll talk about horizontal shifts. Let f of x be one of the parent functions. Then if I change the input to x plus some real number c, then I can create a new function g of x that is f of x but shifted to the left. For example, if f of x is the quadratic function and I change the input from x to x plus 3, then I've created a new function g of x that is the quadratic function but shifted to the left by 3 units. In the same way, if I change my input from x to x minus some real number, then I create a new function g of x that is f of x shifted to the right. For example, if f of x is the cubic function and I change the input to x minus 1, then I've created a new function g of x that is the cubic function but shifted to the right by 1 unit. Next, we'll look at reflecting a function. Let f of x be one of the parent functions, then if I tag a negative sign in front of it, I can create a new function g of x, that is f of x but reflected over the x-axis. For example, if f of x is a linear function and I tag a negative sign in front of it, then I've created a new function that is my linear function but reflected over the x-axis. Similarly, if I tag a negative sign to our function's input, then I create a new function g of x that is f of x reflected over the y-axis. For example, if f of x is the square root function and I tag a negative sign to our function's input, then we've created a new function g of x that is the square root function but reflected over the y-axis. Lastly, we will look at stretching and shrinking a function. If f of x is one of our parent functions and we tag some real number in front of our function, one of two things can occur. Our graph will stretch vertically if c is greater than 1, or our graph will shrink vertically if c is between 0 and 1. For example, if f of x is the absolute value function, and I tag a 2 in front of my function, then it stretches my graph vertically by a factor of 2. But if I tag a 1/2 in front of my function instead, it shrinks my graph vertically by a factor of 1/2. In the same way, rather than tagging a real number in front of a function, I tag it to my function's input. Then, a number greater than 1 will shrink my graph horizontally, and a number between 0 and 1 will stretch my function horizontally. When we graph a transformation, we graph each transformation one at a time. We always start by identifying the parent function. Here, the function looks closest to my parent function x squared. Now ask yourself, is there a number being multiplied to our input? No, so we don't have a horizontal stretch or shrink. Next, ask yourself if there's a number being added or subtracted from your x input. Here we have a plus 3, so we have a horizontal shift to the left by 3 units. Next, ask yourself if there's a number being multiplied to the parent function. Here we have a 2, so it creates a vertical stretch by a factor of 2. Next, ask yourself if there's a negative attached to either your x input or to the outside of your parent function. No, so there's no reflection occurring. Lastly, ask yourself if there's a number added to or subtracted from the parent function. Yes, we have a 1 being subtracted from our parent function, which tells us that there's a vertical shift downward by 1 unit.